Good afternoon. I want to get started because today's speaker has informed me she has quite a few slides, so we want to make sure she has an opportunity to get through all of them. So again, welcome to today's seminar. My name is Gaiman Yi. I'm the Technical Director at the I for Energy Center. And today's speaker came all the way from Denmark, 6,000 miles away. She heard such great things about this seminar series that she wanted to come to speak. Anyway, Kathrine Hansen has been working the last 8 years with VK, it's a Danish industrial investment group with a portfolio of over 150 companies in more than 40 countries. She has been responsible for research projects based on defining, testing, and communicating the concept of the active house. Active house is a vision of buildings that give more than they take, and I'm sure she'll tell you more about that in today's seminar. From 1995 to 2009, Ellen was also a researcher and associate professor at the Aarhus School of Architecture in Denmark. She holds I think this is a Master of Architect degree from the Royal Danish Art Academy of Fine Arts. So let's give a warm welcome to Ellen.
Thank you, Yi, and thank you for inviting me. I'm honored to be here, and I'll do my best. I have a lot of things, of stories, of all kinds of things I would like to give to you. I'm not going to show you very many numbers, but I've actually tried to put a lot of people into my slides. And I hope that this will inspire you to work across the fields and inspire you that we keep sharing knowledge in this very, very interesting field. I've split up my lecture in 3 parts: our common future, the background, and then the active house, where I'm going to talk about what is this, the vision, the specifications, the alliance, the experiments. And I will show you 2 cases, a home and a children daycare center, and then I will round up. Our common future is the title of a book that came out after the meeting at with the Brundtland Commission, and there's a quote from this book that says that sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. And I think it's very important to start at this point from 1978, because that was when it was really well known for all of us that this is a common challenge. It's not something that we have to solve individual. It's something that we have to stick together, all of us, to try to solve. I wanted to bring some pictures from Copenhagen. Maybe some of you remember COP15 in Copenhagen. We had huge expectations, and we are proud of this picture. But it was a little more difficult than we thought. This leads me to say that we really have to stick together and keep believing that we have to solve this problem, which I believe is much bigger than we can imagine. We have a European strategy on buildings. As you probably know, 40% of the energy consumption the buildings are responsible for, and the ambition for 2020 reduction in EU is 20% for energy consumption and 20% for CO2 emission. We're also in Europe talking about zero energy building and how the member states are required to develop buildings like this. In Denmark, we have a vision that the Danish society should be independent of fossil fuels in 2050. And we have not a vision, but we have requirements that are very challenging to the building industry, and that is that the energy performance of buildings will be tightened by 25% in 2010. It has already been effected. and by 2015 and 2020, which means at 2020 we have to, our buildings have to perform 25% better than in today. In California, you are even more ambitious. You probably know that, but you are achieving that in 2020 all residential buildings should be net zero energy, and in 2030 all new commercial buildings. Just to put this in a relation to history, this is the building requirements in 1961 in Denmark. This was kilowatt hours per square meters presumed. This was in 79, 95, 2006. This is the average consumption of energy in buildings today, and this is the requirements for new build today. This is where we should be in 2015, and this is where we should be in 2020. So we are very, very low. Until now, we have solved a lot of this by insulating the houses better, making them tighter, getting better windows. But I think this illustrates quite well that we cannot reach the goal by making the walls thicker and the windows smaller. We have to think different. Richard Pierce has made this nice illustration where you can see this is the non-renewable sources. These are the renewable sources. And here you can see the solar energy. It's enormous, and it's so important that especially you as students really consider this not as limitation, not making these houses where we are closing ourselves in, but look at it as new possibilities. You probably know, but we have to remember that the sun is supplying the earth with 15,000 times more energy than we consume. And this is my child when she was 2. I changed the subject now, no. She has found this spot by herself. Mom was busy. She found this Donald Duck magazine and she placed herself here. And this light is coming from a north-facing window. The light is being filtered through the leaves from the apple tree outside the window. And this is quality. And this window in our house from the 60s would not have been built like that if it had been considered in energy optimizing programs. And that is my approach today, that we have to be very aware of thinking these qualities together, because we cannot lose the qualities of how do you make the good spaces. These are students from the School of Architecture in Aarhus. And if you look very carefully at this picture, they are looking at a future solar cell. It's called the Grätzel cell. It's made, we call it 3rd generation of solar cell. Doesn't matter. They're looking at this panel. It's transparent. But what's interesting is working with these transparent panels have some also aesthetic qualities. I don't know if you can see it in this light. There's actually quite a lot of light here. But if maybe you can see that the mirror in this panel is actually the mirror of the two bodies together. So suddenly you see something different, and suddenly something different comes out by using the glass in an artistic way. You are really observing how is the light. Oh, that's better. Transmitting, absorbing, and being reflected in this technology. And this is where the daylight and the product technologies and the people meet. And it's so important that we develop the technology and we develop the products in a way where it's not the technology for the technology or the product for the products, that we develop this to make spaces for people, and we are aware of what these spaces do to us. So it's very important that we learn when developing these technologies and products that it has to do with what do these people have of impact on people, and not isolated how do these products perform. And this is a space Another way of looking holistic at this is this active house vision. It came up because we thought it was about time to define. We know there's a new paradigm, and we would like to put words on this. And we thought, what if you could imagine that the future buildings give back more than they take? That must really, referring to the Brundtland report again, that must really be the goal, that living in our houses, we are not taking more than we are giving back. That's the vision. To look holistic on this, we look at the energy parameters, and looking at the environment, you have to look at the environment in a whole, you have to look at life cycle analysis, but also look at the social and cultural environment. We made specifications, the first edition, and we have this, the specifications are quite complicated, but there's this spider net where you quite easily can check your house and how it's looking in these categories. There's a home page where we try to exchange the knowledge. And the VKR holding group is owning companies that are making roof lights, vertical windows, ventilation and indoor climate, and solar thermal energy. And a company group like this has a challenge, because this is a standard building, this is where we should reach, and now we can see, now we have insulated all the houses, now there's a challenge for the window industry, there's a challenge for the thermal bridges, the air tightness, the ventilation, and the solar thermal. And the board of VKR Holding decided 4 years ago to do something and take action by financing 8 houses built in according to the active house vision in 5 different countries in Europe. And the companies VELUX and VELFAC and Sonnenkraft have been project managers on these 8 houses. I don't know if you read, some of you have read in Financial Times this week, a Russian active house was mentioned there. But these are European. This is a Green Lighthouse. It's placed in Copenhagen. It's a round house. It's built together with the University of Copenhagen. The other houses are one-family houses. This is built by Sonnenkraft in Austria. This is in Germany. Sonnenkraft do make solar panels, and they thought it was interesting now they could design a house which would really focus in on how to optimize the solar panels. And since we need the solar energy during the winter when we need to heat up the house, we can make actually the best angle for the panels is that they are very vertical, and this shape is actually optimizing these, and some new architecture comes out of this. This is from Austria. And Germany, this is a renovation of a semi-detached house. This is the existing house that has been renovated, and this is an extension that is generating the energy for the whole house. And this is in England, just opened a couple of weeks ago, and this is from France. The house I'm going to talk about is the first house that was developed, the first house of the 8, the first active house, and it's from Denmark. I was so lucky to be the project manager of this project, and it was really, really interesting putting people together and asking them what could we do to make a house that will make a difference, a house that we will refer to as this is the direction that we should go for future buildings. And you can see the group here at the first meeting, they're pointing in all kinds of directions. But one approach in this project is that what was the most important tool for us was that we all the time, instead of discussing should this be energy class 1 or 2 or how many kilowatt hours per square meters. We tried all the time to consider how would life be in this house. And the most valuable workshop was the first workshop where we pretended we gave an interview to 60 Minutes year 2020. Yeah, year 2020. And we were being interviewed, and we pretended that we were the family who had lived in the house for these 10 years. And suddenly the father of the house said that it was fantastic living in this house, bringing up your children in a house where you have not taken more than you have given back. It was also fantastic knowing that the children in your house has been brought up where there was always fresh air and lots of daylight, and where the house is changing for the seasons. And all these quotes were very important for us through the process to make sure that we remember what is really important. Just to, sorry about this being in Danish, but it's just a way to tell you how you sometimes, very simple, can work across the different fields when you design things. And that is that when we in the group were designing things, every time we put in a product or a thing we wanted to do or a goal, we had to define what is the qualities in an energy perspective, indoor climate, and environmental perspective. And it was very, very simple, but it made it so easy in the group to make sure that we all the time considered all the aspects in the group. And of course we also use tools to analyze the daylight. VELUX has a daylight visualizer you can download for free and put in your 3D visualization. And it's so easy to use, and it's so valuable because you can change things in the model and very easily see how it will change the experience of the space, and of course how much daylight you get. And in this house, of course, daylight was an important issue. We had the 4 design parameters. Of course, the house should be orientated to the sun. This is south. And we took the top of the roof, moved it to the north, so we get this big south-facing sloping roof. And we also get a special space in here in the main room. The house is very well insulated, and the house is very tight. And we cut a lot of holes in it, and that's different from, for example, the passive houses. In this house, it was important for us to cut all the holes that we wanted. And we ended up with a window area at 40%, which is almost double as much as you used to have in new one-family houses. And we had different window design principles. We have the south-facing active facade. We have the north-facing rooftop windows, which lets in a lot of air compared to the area of window. We have the east and the west facing big square windows. Of course, also the window and the position is we were very aware of making airflow for natural ventilation. And then a very important thing is that this house is intelligent. It's an intelligent house. It's controllable according to the weather and to personal need. This means that we have a weather station on top of the roof that can measure or register how is the wind, how is the temperature, is it raining. And in every room there are sensors measuring CO2, humidity, and temperature. And this means that the house can, by itself, open the window for natural ventilation. It can turn down the external sunscreen. It knows when to start the heating system, etc. And finally, when this optimized house is done, we put on the technologies that produce the technology or transforms the technology directly from the sun to heat and electricity. This is solar heat panels combined with an air-to-water heat pump, and it is PV, and the house is heated by water in the floor. And the ventilation system is hybrid ventilation. It's a combination of natural ventilation most of the year. During the winter, it's mechanical ventilation with heat recovery. And we are working very hard on the seasons in between, how we can optimize that you get natural ventilation most of the time and not spend very much energy on the mechanical ventilation. And still, we believe that fresh air, smelling the air, feeling the air from the outside is the best way. So this is what we call integrated energy design of the house. The energy, we had an idea that it would be nice when you start a house, the day you start running a house, you have used some energy, the energy used for producing the materials. We calculated to this. We know we are now touching something that is difficult, but we wanted to start the discussion about this. And every year we calculated there would be an energy surplus. And after 40 years, very theoretical, it would be nice that we could say, now we have actually produced not only the energy for running the house, but also the energy we used for producing it. And of course, a very, very important subject is energy balance. How much energy or heat do we get in through the window? How much does go out through the window? How can we optimize this? And of course, working with the window industry, it was possible to use some of the very new intelligent active windows, which is not just a window, it's a very new material we call Halo, produced in Canada, by the way. It's new linings, it's paints that are 2 and 3 layer, depending on what direction we use them. This is the house. You entrance from the north, have an entrance here, you have this living room and kitchen, and the living room here. We had an idea that you should have access from all rooms to the free, even on first floor. We also had a rule that you should have daylight from at least 2 directions in every room. In this room, there's actually daylight from 5 directions. On the first floor, you walk up and you have bedrooms and a bathrooms, and they all have light from the north and have access to terraces. So this building is very compact. It's a wooden building. And the material used, we try to use natural material. This is slates. And here you can see the house from the northwest and from the southeast. You can see the weather station, the PVs, the solar panels, the rooftop windows. You can even see the sun shading on the windows. You can see how they are open on a sunny day like this to ventilate. Here you can see the east and west facing square windows. And here you see the main room, the kitchen dining room. And look carefully now, because now the sunshade is down on the south-facing facade, which means it's not only something you can use to adjust the indoor climate, prevent overheating. It's also something you can use to change the atmosphere in the space. Look and look. And here it's the sun in the evening, the low evening sun coming in. And this is the living room facing west. The windows, since the walls are so thick, the windows are so well insulated, it's possible to sit in the window without feeling cool from the window. And here we have also worked with having this much glass. It can be too much, so you have to be able to adjust it yourself. This is outside shadings. They are not doing anything to the energy, but they are helping to adjust the light. This is one of the children's rooms. This is also from first floor. We are measuring all these houses. We're trying to put it into a matrix to make it a little simple. And we are trying to measure them in the parameters that we talk about when we talk about the active house specifications, the energy parameters, indoor climate parameters, and environment parameters. And we look at the design phase and the numbers from there. We look at the operation phase, and then we look at the analyzers. That's the quantitative meters, and we make these reports. What we have found out is that this is very important because these houses that have to perform so precise, it's really, really valuable to have these reports when we are commissioning the houses to make sure, not to make sure, we could see that there's a lot of things that you really have to be aware of. And these monthly reports makes it possible with very short intervals to be able to adjust, especially an intelligent house like this, so you optimize it quite fast and before that the people in the house start overruling the system. But we also try to measure the qualitative meters. This is an anthropologist, Johanne, and this is Sverre, who's living in the house. And I love this picture because he thinks that she's looking at the numbers on the screen. And of course she's observing how he, as the father living in the house, actually is being in an intelligent house and a house where all the data is being collected, and very proud when he can see that the house is giving more energy than they are using. This is the family, the first test families living in the house. 2 months after they moved in, she gave birth to a child, which gave us a lot of other challenges because then she was home. I'll try briefly to give you some of the lessons that we learned from the first year. We were happy that they liked all the daylight and then they liked all the fresh air. And we have actually stories that made it a challenge for us to switch to the mechanical ventilation, because after doing that, when it became winter, the mother in the house started opening all doors and windows because she had gotten used to the fresh air and she thought that was really nice, and she had learned that that was very good for you. And we could see on the PPM and everything else that the indoor climate was perfect. So we found out that there's really a lot, it has a lot to do with habits. But we can see that it's very important, as I said before, having these big glass areas and having especially glass areas facing south. It's very, very important that you have the south-facing sunscreen and that you are really, really focusing on using the natural ventilation in the right way. We can also see that these houses with 100% south-facing facades, actually it's not giving you what the calculation says because it's too much. Actually, it would be valuable if we could take some of the glass area and move it to the north so we could get a more even daylight in the house. We can also see in this house we were not sure if we should use heavy heat accumulating materials because we were afraid of if it was too difficult to get rid of overheating. But we are now convinced that it is right to use heavy materials in the inside to make a more stable indoor temperature. Also because the heating system is very slow, so it's not something that you can adjust fast. And then we really, really noticed that it's a challenge, especially in houses, to create the balance between the automatic control and the opportunity for the residents to control the house. And we are now aware of the challenge that it's not a matter of the people not using the houses right. It's a matter of being aware of what do the people need and how can we design houses, how can we design technology that push the people to get the right habits and to motivate people to live in the right way. Indoor climate, this is energy. The first year the energy consumption was higher than we expected. A lot of it had to do with the user behavior. Some of it had to do with the control and technology. Some of it had to do with the building and the tight net. And this leaves us to focus very much on the behavior in the houses. It also has learned us that you, of course, should check the tightness of the house before it's done. So that's this was built 3 years ago, and I mean, so many things has happened in the tradition in Denmark, and now I think a lot of people have learned how to manage this. So now we are not talking about how you calculate a house. When we did this, we actually calculated the house of what we expected after the methods that you use for getting permission to build a house. But now we have found out that we have at least 2 different calculations. We have the calculated, which is for the government, and then we have what we actually expect, which is not exactly the same, and then we have what we measured the first year. So this leaves us, this is easier. Here you can see what we have calculated. This is actually what we expect now, because we have known now that the calculation used for legislation is not very good for what you can expect. And this is what we measured the first year. This is the reason why there's a difference, and this is what we can optimize, and that's why we should end up here. And unfortunately, I don't have the numbers for this next year, because they're almost there, but not yet. Another thing you can go and look up at the Active House site is that we have some technical reports reporting all the numbers about the indoor climate, if that has your interest. And this is a report where we try to analyze the house as a poetic device, technical tool, where we look at the windows as design parameters, the south-facing window, the east and west-facing, the north-facing windows, and we try to analyze the poetic aspects and the technical aspects in quotations from the families living in the house and from the anthropologist and the different measurements. And we find out that they do not always support each other. There are contradictions, and it's very, very important to be aware of these contradictions, because that's the challenge, and it's not a matter of either nor, it's a matter of discussing and putting this up to each other. And we're hoping to share this knowledge on a site soon, which will be part of the Active House site. And a project like this is very valuable for legislation, because we have a case, we have numbers, we have test families, we have universities that are testing the house, and that means that the poor politicians in Denmark who have to make the legislation, and it's so difficult because where can we set the goal, really need examples, experiments like this to make us all a little more what's called released in how the future will be. I think I'll make it. Okay. This last case I wanted to show you because I like the approach about how you can design houses, which is actually depending on energy parameters, and suddenly something completely different comes up. And that way it becomes really, really interesting, making sustainable architecture. It's a children's daycare center close to the VELUX and VKR headquarters in Denmark, actually on the other side of the road. This is facing south, obviously. And this is also an example of an integrated design process. And the idea is that we have this 3-angled building plot, and what do we put up with this? And you can make this 3-angled house. It's a very compact volume, but you all know that it's quite difficult getting a nice space in here in the middle. And what do? We have just learned that it's very important to have windows facing south to get all this energy from the south. But if you instead make a roof that is sloping south and north and put it on top of this that is facing southeast and southwest, you suddenly get some very interesting facades. And you get a very interesting roof. And you get a plan where you can have all the these 7 rooms for the kids. You have some spaces around, which is almost like in a village. You had the administration. And you have activity rooms here, and this is where all the kids sleep outside in a pram. That's very Danish. I will not come into that. Here you can see the facades. And here you can see the roof. It's like a plane. And here you can see how it's put down on top of the plan. And what's interesting is that suddenly all these sections come up by themselves. And that's where it becomes interesting, doing integrated energy design. Because all these group rooms, these 7 group rooms, they are exactly the same in the plan, but in the section they are so different. And the whole design of the house was depending on how do you cut holes in the roof, how do you cut holes in the facade to make these houses, or these spaces, have their own atmosphere. And here you see the section, the energy section, still very well insulated, very tight, very much daylight, natural ventilation, external sun screening on the south-facing rooftop windows and facade windows. The ventilation system is the same, hybrid ventilation, natural ventilation combined with mechanical ventilation with heat recovery. And we have pipes in the ground that is supporting the solar thermal energy, and we have PVs to make the electricity. And something that is very important for engineers when you sit in a design group like this is to be able to make figures like this. Because here you can see how they have studied if the roof have sloping or has a pitch on 30 degrees, up here the yellow, or it has a pitch on 20 degrees if it's facing south or it's facing north. And here you can see how important it is that the roof is facing 30 degrees when it's to the south, but when it's facing north, it's much better that it's not that steep, that it's 20 degrees, because the sun is not in the north, not even in Denmark, so here you catch the skylight. But when it's facing south, you catch much more of the sunlight. You can also see that they work with some different panes, the G value, how much light do you get through the pane, and end up by analyzing very, very simple that of course you should use 2 layers of pane with a high G value, so you get a lot of daylight and heat in from the south, and to the north you should have 3 layers of panes. And also this very simple calculation, what happens if in a children's daycare center there are no children during the night, so it's very easy to make night cooling. And here you can see numbers of hours in one of the group rooms with overheating more than 26 degrees during the day, with night cooling, and without night cooling, without having this natural ventilation where the window opens and the construction is being cooled, you will have many more hours with overheating. I forgot to say that all the inner walls in this house are concrete to have this heavy mass to regulate the climate. And now also we have learned that one thing is to calculate the energy for the legislation, another thing is to calculate the energy consumption of what you expect, and that's much more complicated. And I'm not going to go into this, but I think it gives you an idea of how complicated it is. But our measurements from this first half year is actually showing us that it's working. This is the energy demand. I don't think I'll go through these numbers. Oh, go through them? Okay, sorry. This is the energy demand. I'll start here. The energy production. This is what we produce by photovoltaics, solar thermal, geothermal, tubes in the ground, and the heat pump. And this is the energy demand. This is what we use for room heating, hot water, electricity for the heat pump, electricity for ventilation, electricity for appliance, electricity for lighting. Notice how little electricity we use for lighting. It's nothing. And I mean, in Denmark it's dark by now. Half of the year it's dark all the time. No, but of course, being aware of the light in the house and being aware of using the right amateurs, it's you can reach this. Yeah, and we will get a surplus, and some of the heat we will put into the ground to use for the dishwasher, And some of the heat we will surplus. Yeah, this is a surplus, which is the surplus that we could expect. We could save, so it could pay back some of the energy used for building the house. And here it's split up. I think it's easier to understand. It's split up in electricity and in heat demand. And here you can see we, of course, we produce some heat from the thermal heat during the summer that we are not using, of course. And here you can see combined to the legislation. 2008, the requirements, 2010, 2015, 2020. And here you can see that this house will be in a surplus. This is the house calculated without calculating the renewable energy. So this is how the house would perform if there was not any renewable energy. We would get it all from the outside. And here you can see this is one of the spaces in the middle of the house. This is interesting. Also, how exciting it is to design houses when you try to optimize energy. This is the linings like this from the rooftop lights. And look, this is where one of the sides of the linings in the rooftop is angled. So it reflects more of the light. I do it once again. Oh, no, I don't. Look, this is the linings like this, and this is where the architects are creating how you can guide the daylight in different ways by working with the linings. Very effective and very simple. This is a prefabricated wood construction. That's something we've learned now in Denmark because that makes it easier to make the houses airtight. And this is the house and the children and our future. And of course we will try to learn something from this. I think it's very important that, it's easy enough to have visions, it's easy enough to build a house, but really to collect knowledge and use it as a laboratory for studies of well-being, behavior, health, energy consumption and production. That's what we have to do, because the houses and the people are always using the houses different than we think. And one of the studies here is we study the indoor climate. We registrate the indoor climate in the two old institutions where the children came from and the absence of illness. And we do the same in this house, and we try to see if we can see some pattern in this. And this is more theoretical. Can climate-friendly architecture move the behavior of habits of children in a sustainable directions? Is there a way where we can be more aware of seeing this feedback from what the buildings actually do to us and do to our behavior? Because as we can see, the people's behavior in the houses is what really matters now. And of course we also measure the indoor climate, energy consumption and production. And I just wanted to, 2 slides. I've thought a lot about this, and I thought that there are some things that is really a challenge for us. We can build these nice houses now. The really challenge is refurbishment. But another challenge is that we are used to looking at these houses in a 5-year span or a 10-year span, and that's not good enough, because we really have to consider this in a wider span of time. So we have to try to force ourselves, when we talk about these houses, that we look upon them in a 40 or even 100-year span, because the challenge we're facing now is so important. So it's not enough just looking for the next regulation. I also think that we are so, at least in Denmark, and I think maybe it's the same here, that we are very, very aware of regulations and assessments, and it's so easy to judge and to look at houses and how they perform. We actually have a saying when we measure our houses where we say, just imagine if the quality of our houses was measured by their ability to improve life. and not measured on how they perform, but their ability to improve life. And then I think something that is very difficult is the life cycle analysis, because that is what it's really about. Now we can talk about indoor climate, we can talk about energy, but understanding, talking about a life cycle analysis in a big perspective is really, really a challenge. And then I'll end up by showing you this picture from MoMA in New York, actually, by Magritte. Yeah, then I have a quote from Mies van der Rohe that says, if things, oh, I forgot it now, you'll never learn things if it's not part of yourself. And you should see that together with that eye, and I hope that you will all open your eyes a little more so we can keep sharing across the different fields. Thank you.
Thank you, Ellen, for a wonderful talk. Let's open the floor for questions. There we
go. You touched on briefly on how important it is to match the house to the residents and to motivate the residents to use the house properly. There was an interesting presentation 2 days ago here, which showed compared 4 cities where they had built these houses, and there was 3 of the cities houses performed much worse, and the 4th city, I think it was Vauban, the houses performed much better than expected because the residents had been involved in actually designing the houses. So I wonder, it sounds like you've been designing the houses and then adopting the houses to the residents. Have you thought or have you worked with actually incorporating the residents in the design process from the beginning? And have you had any results in that way?
Yes, in these cases we have not had the residents when we did the houses, but we actually did a big efforts trying to pretend that we were the residents, and we actually made games where we made up families that we believed would live in these houses. So we tried all the time to put us outside the position of being people who build a house, but being the people who live in the house. But one thing I would like to mention is that I also heard the lecture Wednesday, and it was very inspiring, because I'm convinced that that's also one of the challenges, that we should not build individual houses that perform fantastic. We should start making communities where people go together by performing together, because that's something that will be much more powerful. And I also think that will really encourage people if they feel they are part together about doing this. So that's something that I really think that we should start focusing on now in step 2. I think we just had to start somewhere because it was difficult just to make an Energy Plus house. But I agree with you, we should try to use them much more in planning the house.
We should have something called active community.
Yeah.
I was just wondering about the airtightness, what airtightness level you got to eventually. I mean, what you decided to, because it sounded like you started with one target, but then you switched to a different one, more tight.
Yes. Oh no. I'm so sorry because I don't know. It's 0.6. Do you know? Yeah. And the airtightness is usually between 0.6 and 1. The problem with the first house was that we had this target, but we forgot to check it when the house was under construction. So afterwards we could see that the house was not that tight, and we thought, well, what matters? But it really did matter. So now we learned the lesson that it is very important that you, during the construction of the house, is very aware of the tightness of the house, and we have an aim that it should be on passive level or a little higher. Sometimes when you have actually a lot of windows and you build a lot of components together, it can be a little more difficult.
Really great talk. I wanted to ask, though, if you're getting the majority of your power from photovoltaics and solar thermal, how do you plan to deal with intermittency or off-peak power consumption?
What? Humidity?
Intermittency. So if the sun stops shining or if the clouds cover.
Yeah. Good question. I forgot to say that in Denmark we have when you produce electricity and PV, you can transport it directly to the electricity net and use it as a bank. And when you need the electricity, you can get it again. Because in houses like this, and especially in Denmark, we produce most of the electricity from the PV during the summer. Then we put it out on the net and we get it again. So the total energy performance on the house is for a full year. Was that an answer?
What is the cost of these houses compared to a traditional house when you take the energy savings into account?
Good question. We have a developer who contacted us and is trying to build the home for house at a really low cost. And we are working on the home for house was an experiment, and we were not very focused on making it cost effective. But the kindergarten was built by the municipality, it's called that, the town. And it was their money, and it was built for the budget that they usually have when they build kindergartens. Some of the very advanced technique is still a little too expensive. But I'm sure that when we learn to build these houses and when the products gets more common, it will not be a matter of they being more expensive.
We'll just make this the last question.
Your discussion of ventilation seemed to assume that outside air is healthy and clean, but I assume in many parts of the world the outside air is so polluted that something needs to be done to clean the air before it's introduced, and that adds more cost. And so I'm wondering whether the whole strategy for dealing with ventilation might change in such environments.
Yeah. It must. That's a very complex question, and I don't know the answer. We're so lucky in Denmark that most places, except for noise for traffic, we don't have that challenge, or in Europe. But of course, I think as the same thought as that house is giving more than they take, you should also say that the indoor climate, of course, is better than the outside. Usually we say it should just be almost as good. Of course, we should manage that the facade as a filter can ensure that we have a better indoor climate. But it's not something that we have been aware of. We have, I must admit, assumed that the direct fresh air is better than the ventilated air.
Okay, great. Thank you very much, Ellen, for a wonderful talk.